So yeah, we're excited to have a panel discussion now. Let me just take a minute and check if all of the panelists expected are here.
Great.
All right. Yeah. So
everybody's here.
Yes, that's right. Sanya just couldn't make it today. She's not feeling great, but it's gonna be all of you on the Zoom call right now. So Ming has gladly agreed to moderate the panel, and so she'll be leading with the questions. And maybe we could also do like a quick round of introductions, but yeah, really over to Ming now, and very excited to see how this goes.
Okay, so I would like to, I'm not sure everybody's seeing the same thing as I do. So I'm just gonna do, so this is how we're gonna run this panel. I would like a quick round of introduction by everybody, and then just say your name. And then what I'm gonna do is I'm gonna come back to each one of you, have you give an open remark on what do you think differentiability is useful and why not the alternatives such as just simply computing the gradients. Okay, all right. So everybody knows who's who. CJ, do you want to start? Just say who you are and you know where you are.
Hi, I'm CJ Taylor. I'm with the Grasp Laboratory at the University of Pennsylvania.
Great. Bethany?
Hi, I'm Bethany Lesh. I work at Argonne National Labs, specifically at the Leadership Computing Facility, which is our supercomputer facility.
Okay. Wami, go ahead.
Hi guys, I'm Yuan-Ming, and I am a fourth-year PhD student at MIT CCL. I work on graphics, simulation, and compilers.
Thank you. Leon? Leon, are you there? Can you unmute?
Liam, we can't hear you.
We cannot hear you.
Maybe we just go to some of the others and then wait for Liam to just.
Okay, we can see the Leon's face, and we'll come back to Leon later. Andrea?
Hi, my name is Andrea Tagliasacchi. I'm a research scientist at Google Brain, and I also work at U of T.
Okay, great. Peter?
Hi, I'm Peter Battaglia. I'm a research scientist at DeepMind.
Thank you. Dan? Dan, are you there?
Yeah.
Can we see you? Okay,
yeah.
Go ahead.
Yeah, I'm a graduate student in the Center for Theoretical Neuroscience at Columbia, and I came to listen to you guys speaking.
All right. And Joanna? Are you there? Yes.
Hi, I'm here, but I'm an organizer. I'm just helping moderate.
Okay, Kelsey?
I'm similarly here, but I'm an organizer helping moderate.
Okay. All right. So what I am going to do is once we have a very brief introduction, I am going to just pass the mic to each one of the panelists and have each one of the panelists share with us their personal perspective regarding differentiabilities and, you know, versus other alternative approach. Okay, CJ, go ahead, please.
Okay, wonderful. So I guess what I'll do is actually echo a point that I heard in your talk, because it resonated with me. As at Grasp Laboratory here, we work a lot on robots, actually stuff at the intersection of computer vision and robotics and the like. So this concept of being able to build differentiable models to help us model actual robotic systems that we have. So for instance, you know, these legged systems that are walking around in extremely complicated environments where we don't have wonderful models to begin with. I think it opens up the opportunity for us to both learn models that have better predictive properties, but also allow us to get at control, which is what we really want to do. Is how do we have really performant systems that work in a lot of these environments where our existing models are, quite frankly, at this point, less than adequate.
We can't hear you, Ming.
Sorry. Thank you, CJ. That's a very brief introduction of your perspective. Okay.
I
Thank
figured there's a
you.
lot of people.
All right, Bethany, would you like to say a few words regarding what your perspective on differentiability and why it is useful, and you know, what's your view on the what's your perspective on sort of compare that to alternatives?
Sure. So my background is applied math, and I've been working on machine learning for dynamical systems, and more recently a little bit of fluids. And I have not done any vision, just to be clear, but I am learning a lot from you, the rest of you today. And I really like the idea of being able to integrate your physics simulation with your machine learning as an end-to-end pipeline. And I've definitely had personal experience with estimating gradients directly from noisy data can really amplify noise. So it's great if you can analytically compute gradients. And something I'm thinking about today is that our supercomputers, we have computers coming that are going to be primarily GPUs, and I'm wondering if differentiable physics approaches to simulations could take advantage of the GPUs.
I think so. I think it can. And that's definitely another direction that we can move toward as a community. Okay. Wang Ming, would you like to go ahead and say a few words?
Sure. Yeah. So first, I would like to answer Bethany's question. So can differential physics leverage GPUs? And the answer is yes. We do have a Tai Chi system that can generate code for both CPU and GPU system. And you write the code in Python, the compiler will generate GPU code for you. So it's an easy way to somehow leverage GPU resources nowadays. And my perspective on differential physics is that, first of all, I really like it. And we have seen for certain problems, by utilizing the analytical gradients, the optimization will just run ridiculously fast. And compared to reinforcement learning, we have clearly very, very huge advantage here regarding exploitation of existing strategy. But there's one thing that I want to highlight, which is according to our experiment, we do find that differential physics tend to get trapped in local minimum, just because now we have much more accurate gradients. And if the real gradient is 0, then it's 0, which means you're not making any progress there. So that's one thing. And the other thing I think differential physics can actually help us solve is on more the connecting virtual and reality world side, because nowadays a lot of people, especially robotics people, are really, really interested in how to reduce the sim to real gap. And apparently differential physics allows us to somehow combine the real world data from real world experiments with the simulation data. And by doing this kind of optimization, we can do hybrid simulators that can close the sim to real gap. That's my humble point.
Great perspective. Thank you. Leon, are you there? I'm not. Yeah, great. Okay, we got you. Okay. Actually, talking about organizer, I forgot to introduce one person, but I think that person doesn't need introduction, and that's Krishna. Everybody say hi to Krishna. Okay. All right. Thank you, Leon. Okay. Actually, you know what? If you are here, you cannot escape. We are going to come back to both of our organizers to ask them for their opinion at the end of this. but we will reserve the space for them at the very end, the honorary position. All right. Peter, can you hear me? Peter?
Yeah, thanks. Yeah, so I mean, I guess I would say that you know, optimization is it's some kind of search process, and differentiability offers really efficient ways of can drive algorithms that are very efficient at searching. And so, like, I think that's also underneath a lot of what the benefits of say even just training neural networks with backprop rather than some kind of like reinforced algorithm. Right, this is the root of that. But another thing that I talked about in my talk that I think is an important thing that we can sort of exploit about differentiability and auto differentiation is like I was showing a few projects where we're taking physical relations from physics that sort of relate, say, like the partial derivatives over spatial quantities to the time derivatives, and we can sort of efficiently calculate gradients using JAX or TensorFlow or whatever, and then and put those inside our model, so we can sort of exploit these inductive biases from physics very easily with a few lines of code, and then we can do things like Hamiltonian mechanics, sort of build that into our model. And get all sorts of energy conservation and different types of generalization that we're interested in. And just the last thing I wanted to say, addressing what Yuan Ming said about the sharp gradients, I think that an interesting direction we should be thinking more about, and I mean, some people are thinking about this, I think, have thought about this for a while, but yeah, like these really accurate models with these kind of like very detailed gradients, if we're trying to optimize something, that's not actually what we want to optimize. What we want to optimize is a convex function that happens to have the same global minimum as that function, right? So I think that thinking about how to, take very accurate forward models, or maybe even knowledge of the gradients of those, and come up with other models that are going to support even more efficient search could be, very good for us in the future. So that's all I would say. Thanks.
Thank you, Peter. That's really interesting thoughts. Next, I think I'm going to go to Andrea.
Yes, can you hear me?
Yes, go ahead,
yes.
Please.
I guess my perspective is a bit different. It's less from the physics side and more from the robust computer vision side, where I've both worked with estimating noisy gradients from data, as well as more analytical gradients from whatever forward process you have. I think the most interesting thought in regard to this particular topic that I have is actually via meta learning. So I think meta learners are something that is particularly this year becoming a bit more popular, I guess, starting from the vision side in being able to estimate gradients by examples. And in that sense, basically you have stochastic estimates of gradients, but then at test time, they actually behave in a very smooth way. So it reconnects a little bit to what Leo was saying a couple of seconds ago. So that's what I think is an extremely interesting part. Is like there is this divide where you could do it by full differentiability or just gradients, but it's actually not true. There is a continuum in between the two different domains, at least in my side of the problems. But
interesting perspective as well. Great. So Georgia, would you like to say a few words? Actually, we missed your introduction, so please, state your name and your current affiliations, and then your perspective.
Sure. Yes. First of all, thank you for inviting me, and hi to everybody else. So my name is Georgia. I'm a research scientist at Facebook AI Research. I have been and I am still a computer vision researcher, so I care a lot about computer vision problems, in particular object recognition. And I am an empiricist at heart, so for me, whatever works is great. And so in terms of that and trying to make object detectors and recognition work better and better every day, we have been exploring whether differentiability in 3D could help us with understanding 2D and not just for 3D tasks. And this is, I think, my interest and why I am here and the perspective that I have. The verdict is not out yet. We don't really know how to make our detectors and recognition systems work better. Is it data, annotated data? Is it better representations by going to 3D? Is it better optimization? We don't know, but we're exploring. And this is what I'm interested in.
Okay, great. All right, so if the organizers are here, they are not escaping. I'm putting them on the spot. Sorry, Krishna, your thoughts.
So yeah, like in terms of differentiability, or like my thoughts usually were, if we've spent years of research just developing, techniques like rendering or multiview geometry or physics simulation, why just throw them all down the drain and like do, I don't know, model-free learning? So yeah, my forays actually started from that perspective. Like, can we somehow try and use all the knowledge that we already have and instead improve systems rather than like replace them? That's where I see differentiability is a very strong scheme. But I don't see differentiability as the end in general. Like, I think there needs to be a blend of things that you can specify differentiably, and there's always things that you cannot specify differentiably. You need to learn them. So there's like a hybrid that we need to shoot for.
I agree. All right, Leon, what do you think? Great. Okay. All right. So I am wondering if the panelists can comment on what do you think, what are the name your dream application that you think can sort of unify. I think I already started mentioning some of that in my comment when Krishna asked me. What are the possible application? So let's kind of start dreaming together. What are some of the possible applications that can unify vision, graphics, physics community together that, different community with different background can achieve together, and machine learning, of course, right? That cannot possibly do alone by itself. So what are some of the dream possibility and application that you can think of? Based on sort of the conversation that we have so far, that you think will be really exciting and challenging, and that actually require vision, graphics, physics community to work together. I'm sorry, machine learning. I keep dropping it out because it's kind of taken for granted. Everybody is using machine learning now. So how can we, these multiple community work together to advance one or two or three or whatever X number of application that is not possible earlier? So I'm going to put, I'm going to just kind of go around in a round robin fashion. Going to put CJ as our first. I'm going to put him on the line and ask him to to share with us his thoughts.
Okay.
CJ, go ahead.
I think this is actually something that Georgia picked up on, but this vision, no pun intended, the idea of the vision being sort of the inverse problem of graphics is something that I think has been around as an idea in the community for quite a while. But I think the kind of techniques that are being discussed here, where, as you said, there is graphics acting as this forward engine, but then allowing us to interpret images in terms of being able to use these tools to actually pull back out meaningful or salient representations, I think is could be a fun thing to take another crack at.
Okay. Should I go around one by one, or is there anyone who want to jump in?
Can I jump in?
Yeah, go ahead.
Yeah, so thanks for letting me jumping in. So actually, I have 2 cents on this. I still believe that robotics application will be a really, really great application of what we have developed here, including differential vision, graphics, and differential physics, because I think nowadays a lot of robotic applications are still based on traditional control methods. And apparently, as we have shown in our recent work in differential physics, we can already just use brute force gradient descent to, on one hand, first make robotics training much faster, because now using gradient descent, it converges 1 or 2 orders magnitude faster than reinforcement learning. And secondly, I do believe that somehow closing the sim-to-real gap can be one very meaningful application of differential physics, because there are just so many ways to inject errors in physical simulators. It could be one model that doesn't really reflect the reality. It could be one wrong physical parameter that is system identification. It could be something numerical errors where a deep neural network can actually correct. So I think those two topics, like accelerating learning and closing sim-to-real gap, are what differential programming is really good at. And I think both of them have great applications in robotics. That's my 2 cents.
Great. All right. Anyone else want to jump in next?
Here, I'll say something.
Okay, go ahead. Go ahead, Peter.
So I think the most important problem in AI is construction or tool synthesis. So I think partially is because I might be biased, but I think this is also one of the most important parts of human intelligence. I think it's sort of what, in some sense, distinguishes us from other forms of intelligence. And I think that when we try to attack the problem, we start to think about what does it take to just to build some building, or even just like fix something that's broken in our house. You're immediately faced with this enormous search space. And so the question is, like, physics is a small set of rules, and it can give rise to a tremendous amount of it can be realized in infinity of sort of different scenes and different scenarios. And how do we search through that, and how do we sort of find things so quickly that kind of work, and what's that process that we use? And then the reason I think that can also be sort of tied into graphics and vision is, so there's this paper I like from Sandy Pentland and Ted Adelson from about 25 years ago or so, where they're talking about, it's about like perception of shading, sort of vision, human vision, perception of shading. And they talk about this workshop metaphor. And the idea is, like, how would you build, it's like this very generative approach to vision. So like the inverse graphics thing was mentioned a minute ago. How would you build this scene out of components? Like, how would I build this scene out of, I have a phone here and I have like a book over here. So in some sense, it really is also a construction process, even to form an interpretation of what's around you. And I think that some of this, say, similar challenges are at play here. And this is an old idea, right? Of course, like even like people like Irv Rock and perception have talked about this for the logic of perception. But I really think that one thing that we probably could spend more time on in machine learning is thinking about representations that support sort of a lazy, almost sparse generation of structure and of hypotheses or solutions, because that's really how the world is organized, and that the problem that one of the most important problems that humans face, and that I think we need for AI. I think vision, graphics, and physics have a lot to, like, learning and exploiting knowledge of these things has a lot to say about that.
I agree. Andrea, Bethany, or Liam?
Sure. I guess that from my point of view, like in putting the 3 fields together, right? Often I ask myself the question, I look at my daughter and ask myself, she has, when she was 1 especially, she can navigate in 3 space without any problem. She can grab objects, manipulate them, perform significantly better than any robot that you've ever seen. And when I'm looking at her, I'm thinking, what kind of media was she exposed to? Was she exposed to 14 million images, ImageNet, right, with labels? Maybe less, right? But then you might ask yourself the question is, like, what if you have a child that doesn't have verbal communication, like an autistic child, right? Will they be enabled then to operate in 3 space? I'm not an expert in this area, but my gut feeling is that that will be uncorrelated from the ability to perceive and operate in 3 space. And therefore, the question becomes, what are we allowed to provide neural networks as inductive bias to actually learn what the world looks like? And the more and more I think about it, the more and more I'm convinced that the only inductive bias that you're allowed to use is physics. And this comes in the form of either simulation, because these are the laws of the universe, right? You know that they are valid. You know that whatever you're doing, as far as you're introducing them, they cannot be violated because they're just there. And if you look at some of the progress that has happened over the last year, some of the biggest advances in differentiable rendering, what have they done? They have just respected physics, right? They have respected, for example, modeling of transparent media. That was scene representation network and neural volumes, and then NeurIPS. They did exactly that. They've done modeling of light scattering events with light fields in NeurIPS. And I find this pretty inspiring. And I think a lot of my agenda right now is driven is like, okay, this is the only, if we're to build the computer vision and the differentiable physics of the future, this is the only thing that I'm allowed to use, and everything else is just cheating. And it might be okay for the time being, because you might still build products and companies and applications, but it's still cheating. It's like you're allowed only to give a network what a 2-year-old or a 1-year-old has access to.
Okay. All right. Georgia, or actually Bethany? I think Bethany want to say something when Andre.
I'm curious if vision can be helpful in climate modeling or weather or other environmental problems if we have satellite imagery to augment incomplete physical models. And something I'm curious about, but I am not knowledgeable of the available imagery data sets.
I would imagine so. I would imagine so. Of course, climate, it's now you're talking about, large scale eddy simulation. So it's much bigger. And that's actually an area of a tremendous potential, because we're looking at climate change and at a global scale, bigger than ever before. That's really a great application.
Yeah, and I will say I'm aware of early work that's been done, for instance, in looking at satellite imagery to try to estimate fluid flows and the like. But I can certainly see an application for marrying this with a physical model underneath it to help us do a better job of interpreting that kind of data. I think that would be a very profitable line of research.
Yeah, and that's really, I mean, that's an area of potential impact at a very large scale. I mean, we're talking about global scale, right? The world scale, and it particularly combined with, like I say, large scale eddy simulation that kind of track how the fluid flow of atmospheres and how that would evolve together with just centuries of data. And I think that it would be really kind of interesting. I just don't know anybody who's working on that, because this is many of the work in this area. It's mostly done by people who are in academia and industry research labs. I don't know how many. I mean, of course you are in national lab really are thinking about taking the latest research and really pushing it forward, to solve some of these really important problems at the national and the world scale and the Earth scale. So that potentially will be of tremendous impact.
Yeah, the national labs are definitely talking about how to use machine learning methods on these kind of climate type problems, but I don't know about from the graphics or vision perspective, if anyone's kind of crossing those fields.
I'm not aware of any. I mean, this is why the panel discussion is so interesting, right? Because we all bringing our different perspective. So this is really, really interesting thoughts. Okay, that is, keep that thoughts. We'll follow up. Georgia, would you like to say a few words and what you think are your dream application?
Yes, of course. I mean, a lot of the things that people have said so far also are part of my interest as well. I'm also trying to, like, just from what Bethany just said, it's always, I think we should actually be thinking more globally in terms of what it is of these applications and what it could be of impact. Of course, we all want to, build models that operate like the human brain, that like they're very intelligent. And this is something that we might achieve, but we also might not in this lifetime. But there is definitely a lot of good gain from building models that tackle problems that are beyond the scope, like climate change, ethics, all these topics that are sometimes less brought to the forefront. So that's something that I would like to see more of. I would like to see more attention and more examples and more research on these type of problems that affect all of us right now. And then like, I think that I would like to, based on what Andrea just said, how do we envision of training these systems if we want to reach this golden standard of I have now trained like a human brain or like another brain of that level of understanding. And I'm not settled yet as to what is the right approach, whether we should simulate how humans learn, or whether we can take a just different approach. Humans had like billions of years to establish how they learn. It doesn't mean that we need to stick to that. There might be other avenues, other paths. Not that what we're doing right now is anywhere as effective or as pretty as how humans learn. That's like very far from reality. But these are all sort of the questions that go in my head and what I would like to see us tackle in the future.
Great. That's good. That's great. Leon or Krishna? Leon, go ahead. Do you want to say a few words? Great. And Krishna, do you want to say a few words? What do you think? What are your dream applications?
There's plenty, but to be really brief, I think I'd really love to see all of these communities working together. It seems like a lot of these goals are shared, but the kind of work that happens is very, very disjoint. And that was the motivation behind this whole workshop, to try and see if there are synergies, like can the differentiable physics and rendering communities interact. We've already started seeing that a bit, and we've also seen synergies between the computer vision and differentiable rendering communities. So yeah, I'd like to see all of us working together.
Okay, we'll be starting to write joint paper after this, right? Okay, sounds great. Okay, anyone else did I miss anybody who want to say a few words about what are their dream application? or even audience, you can always chat. Okay. If not, we're going to move on to the next question, which is, do you think differentiable pipeline or programming will make model-free methods obsolete? What do you all think? Anyone want to volunteer to jump in?
Yep, I can jump in.
Okay.
I think the current situation is, I think there are two things. The first thing is that building differentiable programming models for everything is not yet possible at this point. And there are still a lot of physical phenomena or whatever process that we are able to simulate forward, but back propagating can be very, very tricky. So that's my point one. And my point two is that actually, okay, I think I forgot my point too. Okay, so I'll jump in again when I come up with my point two. Okay.
Okay, we'll come back to you. All right, CJ.
I guess I have something that's hopefully at least tangentially related. I want, this is in reaction a bit to a point that Yuan Ming made that I really agree with, that conquering the sim to real gap is of course a primary challenge. But the other thing I would point out is that the robot that you train for is always different from the robot that you go to the field with. Is you're going to go to this field with a robot, there's going to be a short in the motor, the prop is going to be bent, and the model that you worked with, that you trained so hard with, is actually not good on the day. And so I just want to point at this issue that there's a time scale issue, that we need to be able to do this adaptability quickly in the field, like the crows do when they're having a bad day, but they're able to actually snap back into it in very short order. And perhaps the inductive bias induced by these physics will allow us to lower that manifold dimension in a way that makes this possible. But practically speaking, for somebody who takes robots to the field, this is where things break.
So it means we need robustness training. Okay, that's great. This is great. Anyone else? Anybody want to
say? I mean,
yeah, go ahead, Peter.
Yeah, I mean, I think I sort of hope so in a way, but I don't think so. So I guess the issue is that if you have like discrete sort of problem spaces, and you're sort of thinking about like discrete actions, search trees, and things like this. This is harder for this is not clear how you're going to sort of exploit differentiable like functions or pipelines to handle these things. At the same time, I mean, there's like a lot of work on, continuous relaxations of sort of discrete things. So I think, again, like this is sort of in the spirit of the thing I was saying before about like, you don't really care about the sharp function, what you actually care about is the thing that you can optimize well. Again, maybe like we can start to think about ways of taking discrete problems, state spaces, action spaces, and relaxing them or coming up with differentiable functions so we can exploit their efficiency for search and solving our problems that way. So I mean, yeah, in general, I don't think that in the near term I think model-free methods do have a lot of advantages, but in the long term, I think that it's an interesting thing to even try to challenge.
I would agree, but I would love to hear anyone else who have different opinion or even similar thoughts, but they may want to add comments on top of what Peter has said. Andrea, I think you want to say something. Yes, go ahead.
I don't necessarily want to put something on top of what Peter said, but if you look at the way in which people have been looking at differentiable vision and graphics from the image generation point of view, right? What has it been now? 5 years, ballpark, between the first application of deep learning to a parameterized version of something that you can render. And as of this year, we are model free, right? So we still have a model, but this model can be learned in a way that is completely oblivious to what you're actually representing. It has full representation power, and it doesn't matter what you're looking at, it's still going to be able to do it up to a certain precision, right? So I think that if I were to ask something from the people working on differentiable physics, would be, if it was me working, I do have a bit of background in physics, but very little. But if it was me, I would ask myself, is like, okay, can I take everything that I know from physics, like stress tensors, and can I take deformation gradients, and can I take Newtonian dynamics, and can I now apply it to a representation that can be learned completely from scratch without relying on any instantiation of topology, of dynamics, or anything? It's just like you give it examples, and then it just picks it up. And as far as you've exposed it to enough examples, it will be picked up. So essentially the same thing that happened to graphics and vision over the last 2 years, yes, 2 years and a half, according to when you count. But and I've never seen anything like that. Like we know that these perceptron actually represent surfaces, but do we have a model for the formation of a surface that is actually not represented by a mesh or a voxel grid? No, we don't. I think that's a super interesting direction where I will be thrilled to see some progress.
Interesting thoughts. Very, very. It's very. I would agree as well. Leon or Krishna or Georgia, Bethany, anyone want to follow up? Oh, Huaming, did you figure out what your number 2 was?
So I didn't. I totally forget my point 2, but probably I can talk a little bit of my point 3. So yeah. So my point 1 was about for certain simulation, it's either non-differentiable or we don't know how to differentiate it. And I think because I also work on the compilers perspective, so I also care about performance. So it's often the case that for certain simulators that we know how to do very efficiently regarding forward simulation, but for backward simulation, there are some always a lot of like issues on computational efficiency. I think as Professor Lin just showed that certain simulators are just not as efficient as people might think, and also the memory consumption can be one issue. And so that's why I do believe that developing high performance compilers that are more suitable for modern computer architecture and suitable for certain problems is super important, because only if we scale up the simulation resolution to a very, very large scale can we reasonably good approximate the world. And I actually do have a point 4. So the point 4 is why I do think probably sometime in the future people will like differential physics. So that is basically because I do think human brains has something like a built-in differential physics inside. Just because recently, there's a COVID, and when I'm outside, I cannot touch anything. So I can always magically come up with ways to operate stuff without touching anything. One example is that now I learned how to gently operate the elevator using my knees without using my hands. And also, if I want to open the door, I learn how to use my elbows instead of using my hands. So if you look at reinforcement learning, it will take a lot of trial and error to for an agent to learn how to do that. But if we assume that there's something like a differential solver in my brain, I can just maybe do some mental and model-based attempts, and then I can get some feedback, and the gradients from differential physics will tell me how to adjust to achieve my goal. So I do believe human should learn actually quite a lot more faster than what reinforcement learning are currently doing. And I learned that lesson from George Tenenbaum, and he always says that he doesn't believe like he does believe that human has very strong prior, and human learn things very, very efficiently, and there should be a reason. And maybe to some extent that reason is differential physics, and we would definitely want to adopt more systems that are differentiable in our learning pipeline so that we can learn much more efficiently.
Very, very interesting thoughts. All right, do we have anybody who agree or disagree? Anybody want to follow up on that? That's a very, very interesting thought. Does our brain think like differentiable physics or differentiable vision? Oh, we have a differentiable mind.
I guess I could jump in.
Yeah, please go ahead.
Not to
Georgia.
answer that question, I don't have that answer. But mostly to sort of, actually it's a question rather than a statement, is how will we know? So how will we know if this is the case? So what I'm trying to get to is, let's say that we focus on this one task and we manage to train a system that maybe does this and figures out just how Yao-Ming said, how to just adapt or how to do the same thing in a variety of ways. But we ultimately don't really have a test bed to evaluate whether we've actually learned to think or to perceive or to understand like humans. So I guess the question is, how will we ever know whether we're making progress when we are definitely operate as researchers, we operate in a very task-driven way. We define little tasks, little goals that we want to achieve. So how will we ever be able to know if we actually have unlocked something?
I do have something to say on that, if I am not talking too much.
No, go ahead, please.
Yeah, so I do believe that we ultimately would need something like ImageNet for computer vision, and we do need a very, very nice physics benchmark data set so that people can have a consensus on at least compare what kind of what kind of learning method on differential physics, at least we can evaluate different methods on differentiable physics. We need a common evaluation standard so that we can really push the field of somehow combining reinforcement learning and differential physics together. So at this point, I think the issue is that differential physics are still somehow maybe mostly in the graphics and physical simulation community, and this is kind of a little bit of isolated from people who are really doing learning and robotics. And I do think that's why we need to gather here to talk about future solutions. So I think we really need to make the existing differential physics systems easy to use and easy to benchmark. So that's one very important thing. I do think that the birth of ImageNet as a common standard for evaluating different deep learning system has drastically pushed forward the recent advances of deep learning. Like without a common consensus of which method is better, we cannot push things forward. We do need a good evaluation thing. And currently the issue is we haven't built that common standard yet. And I do look forward something like the ImageNet, something that corresponds to ImageNet to appear in the field of differential physics.
That's definitely a really interesting thoughts, and I would argue the same probably would apply to even robotics, where RL has been used extensively. So we don't have exactly a set of benchmark for robotics community, even though there is sort of a standard list of 12 different robotics, categorizations of grasping, planing, control, and manipulations, and sensing, perception, and so on. So there really isn't a set of benchmark even for robotics, although that due to differentiable physics, now robotics community is using more simulations, and they're sort of starting to have this, like the ants, the walking dog, the mobile robots. So there are some of these models are coming up. So I do think there's a lot of potential there. And vision, it's sort of tying currently to ImageNet, but in the real 3D world where you really need 3D vision, ImageNet is still inadequate, right? Because this is the 3D world, it's much bigger than what ImageNet has captured. But that's really a tremendous it comments that I think that we do need some sort of benchmark in every single community. And that's definitely worthwhile to sort of explore. Now, do we have anyone else who want to comment on whether we think that differentiable pipeline is going to make model-free methods obsolete? I think there is some sort of consensus here. The question, it seems like the answer is no, predominantly. Am I correct? Or do we have somebody who want to argue otherwise? No, we are going to make the differentiable pipeline is going to make model-free methods absolutely. I haven't heard that yet. Okay, if not, we're going to move forward and say, how do you see differentiable method being used and applied in the wild? Anyone have thoughts on this? Do you think we are ready? Do you think how robustly can they run? Do you think?
So I don't have thoughts, but I have context to just add here. Particularly in terms of, let's say, differentiable physics, there are things that you can never hope to model, maybe disturbances like the wind or so, or there might be very complicated objects that you can't always encode in code. And even in rendering, you're always faced with something that's different from the real world. There's always some residual you can't hope to close in. So I guess that's a very interesting thing to consider. Like, do we want these systems to run ready, in the wild on real data, or do we look at other midterm transfer solutions, like you train in simulation and then try simple real transfer? I don't know. Yeah, just opening up more thoughts.
What are your thoughts, comments?
So just some random thought. So maybe surprisingly, I have to say, in many fields, even for physics, simulators are not accurate enough. There are many reasons people can introduce errors in forest physics, including discretization errors and inaccurate model assumptions, and also wrong boundary conditions and inaccurate physical properties. There are many issues, even in forest simulation. So I think, given that, it's fine to tolerate some current learning issues of differential physics or differential programming tools and adopt that in current learning system, because there are a lot of issues in forest physics simulation, but there are a lot of people already using forest physics for computer-aided engineering, for reinforcement learning. So I think I wouldn't say we're 100% ready, but I think what is exciting in the academia is that people are always eager to try new things, and that's why we call it research.
All right. Peter, Andrea, CJ, Leon. Yeah,
Here,
Peter.
I'll say something. So yeah, so I think that this is something I think about a lot, like, how we're going to take a lot of the stuff I showed, we're taking these simulators and we're training some neural network on to mimic a simulator, but that's like sort of easy compared to having something that learns about the real world. And I feel like I haven't really had sort of come to a decision about how we should approach this problem in general. So one thing I've been thinking recently, though, is so I think, just to say, as background, I think a lot of times, for a while, I've been thinking, how do we turn the world, what we perceive with our eyes, into objects and different things that you actually find inside a physics engine, because that's what we need our models to do. And the more lately, I've been thinking of something different a little bit. That instead of thinking about it as it's just a series of representation transformations. So we have whatever our sensors are, collect some image, grid, like a regular grid of little pixels, whatever, volumetric data, whatever it is. And the question is really just, how do we stage, how do we, have a stage of transformations into representations that we want? And what I mean by want is the thing that's going to help the downstream tasks, like was discussed before, or be efficient computation or efficiently learnable. So I think that I'm really starting to think about kind of resource rational, or kind of economically rational way of thinking about how we can just go right from the sensory data all the way through representation and really try to bring in cost of computation, cost of learning, and the cost of whatever your task cost is. And the last thing I'll sort of say on this is, I think it's kind of interesting to think about what scientists do. So like a physicist has a model of the universe or something, and or at any scale, a model of water and particles and things like this. So like there's not actually atoms. Like this is just a representation that's very convenient for us to compute, and it like solves lots of problems, and we can kind of like extrapolate really, really well. So I think it's kind of interesting to just think about the different trade-offs through science and the models that are very prominent and effective and powerful, why those trade-offs were made, and from that sort of get ideas about how we can start to structure our kind of like, again, economically rational choice of representations and computations, where we're going to take our observations of the world and turn those into models. So it's really sort of the same thing. That's all.
I think that's really that's correct, and I think a parallel analogy is probably like autonomous driving, right? We are putting these neural network trained learning to drive module on the street, dealing with the real world, and most of these scenarios are all capturing the very clean data, using very clean model, and now it has to be tested on a while. And so I don't think it will take a lot of learning, but I do think that this is really sort of very interesting things for us to kind of think about in terms of a sort of building on top of what you learn, and your model doesn't have to be perfect. It learns to improve itself through the process. Do we have anyone else who want to comment on this? Hmm. I will totally agree with you. Yeah. Putting into the wild doesn't mean that we're going to put everything into the wild, but it can be used on some application. Definitely safety critical. No, even autonomous driving, it's not approved in California yet, right? Even though we have all these autonomous driving cars. It's largely, I think I heard it's on a fairly constrained environment. It has the potential. Okay, anyone wants to comment on it? CJ? You unmuted.
I think Liam raised an excellent point. And I'm wondering if that then means that looking at systems that would work with the wealth of information we have from control theory, where we do have guarantees and we can make bounded assumptions where the learned aspects are allowed to operate, but within a band that we know is safe based on analysis, might be a profitable way for us to move forward on this.
Okay, great. Anyone else want to comment on this? And actually closely tied to that, let's say that we can put some of these systems in the wild. How do you initialize these systems? Much of these, simulator, render, vision algorithm requires some sort of initialization. What are the way to address this issue? How do you initialize these systems? Either in the wild or even in a laboratory environment or control environment or just simulator. How do we initialize? Do you have these problems? Comments?
I do actually believe that differential physics can have a little bit of benefit on initializing a experiment because I do believe system identification would be a very nice application of differential physics. Then you can basically, based on your observation of something like two elastic balls colliding with each other, and then you do a bunch of gradient descent. It's kind of, you can always infer something like the mass ratio between the two balls. And we did have that in the Chen Qing paper as a motivating example for system identification. So that allows us to actually get a little bit of information from the physical world to the simulation environment by somehow either looking at the physical world or use some sensors to gather some information and then fit a model. So this is actually one area where differential physics would actually has a little bit of advantage.
Great. Yeah. I think Andrea was going to say something.
Yeah, but this is a bit on the wild side, though. I put this prefix on it, but it connects to something that Georgia was saying earlier, right? Like humans had a long time to learn how to behave in the environment, and now you can actually even go to the animal world where the claim is not as wild, but there is behavior that animals have that are driven by instinct. And now you have to ask yourself, what is instinct? Because instinct is nature, is not nurture, and therefore is pre-programmed in the brain. So, and this ties to your what initialization you give to the system. So it's not inconceivable that our visual system and our motion control system are somewhat weakly initialized to nudge you in the right direction. I do not know to which degree, but definitely in terms of just behavior, instinct is exactly that, right? Like just born animals know what to do without any supervision immediately, right? There is fawns that just come out of the belly of their mother and just start walking. And how do you explain that if there's not some form of memory passed down through generations? So But again, this is wild, right? In the sense that we have no idea how to model this, and this will mean like some form of memory in between generations of networks that you train. And the closest thing to it will be like federated learning, where you have these remote model that you update slowly over time. But I think it's pretty interesting. But it's completely wild. Like I have no idea what I have no theories on how to do it.
Well, on that thoughts, unless anyone else is on that have comments, that I think that's a really interesting thoughts that I think we can sit on and think about. And we'll come back next year and we can debate on this, or we can debate over drink afterwards. Okay. I would love to follow up with each one of you individually. We have some really interesting discussion. I think Georgia has to leave already. Also, we have poster presentation coming up. So I would like to sort of, ramping things down. I want to thank you all for an extremely interesting and stimulating and exciting discussion on all these really interesting questions. And I wish we had more time. Unfortunately, we are already kind of running behind schedule, and the poster presentations are waiting. So I want to thank you all for taking your time to chat on this panel format. It has been fun. And I also want to thank Krishna and Liam again for organizing the workshop. So we will follow up through emails or other informal discussion offline. Thank you all for participating in the panel, and thank you all for all your interesting contribution and sharing your thoughts with us in this panel.
Yeah.
And
so Victoria, Kelsey, and Johanna, I think really shout out to them. It is they who did like a ton of the heavy lifting. I was probably just the face, but they did all the work, and it was really nice trying to put this together. And it was nice to just go through all of your talks and have this panel discussion. And yeah, thanks so much for contributing, and thanks for joining, taking the time. And I know it's pretty late in a few time zones from where people joined in. For instance, like Peter, it's probably too late for him. And yeah, thanks so much. We're soon going to start off with a poster session on Gather